and I'm going to be taking you through the session today. So let me just share my screen first of all, and then we can get into the agenda.
Maybe as
Sorry.
cool.
Can you see? What can you see? I hope you can see Canva.
No, it's not Canva. It's Canva.
Yeah, it's Canva.
Okay.
Yeah, just wanted to give you a heart attack here and there.
Okay. So yeah, now let's get into the session for today. And then please feel free to ask questions in the chat or to stop me if you feel confused or you need some clarification. So my session for today is actually going to be on the building blocks of Web3, or what we are calling the creatures of Web3. And just a quick recap on the session that we had yesterday. For those who were there, we had our session with Lance Davis. He looked into Bitcoin, which was probably the very first iteration of blockchain, or a decentralized system that is primarily focused on financial transactions. We also looked at Ethereum, and I remember that we spent quite some time on that. Even Ochi took some time on that as well. We had a brief look at smart contracts and also cryptography. And under cryptography, we looked at zero knowledge proofs just a bit. And if you probably are interacting with all this information for the first time, you might feel like you're drinking from the fire hose. Like, it's a lot of new information. You don't know how to contextualize it. Well, don't worry. That's actually very normal. But if you keep attending the sessions, we'll be able to connect all this information together, just like we're doing today. So today we're actually looking at these building blocks of Web3, 6 of them. There's blockchain, nodes, transactions, consensus, smart contracts, and wallets. So all of these are very fundamental to the functioning of Web3 as we know it. So I think the first thing, that before I even get into blockchain or these building blocks, the very first thing I wanna talk about or explain very briefly is about Web3, so that we can kind of build that foundation. So first of all, I want to say that Web3 and blockchain are not the same thing. I think a lot of people make this mistake when they're starting out, and I know that I also made this mistake, which is thinking that Web3 and blockchain, the concepts are interchangeable, but they're not. So Web3 is an iteration of the internet. So with Web3, that means that we also have Web1 and Web2. So the internet as we know it today is what we call Web2. And before there was Web2, there was also Web1. That was a very, very early onset of the internet that allowed people to access a huge repository of information. So with Web1, the average user of the internet could consume information online. So you could log in to the internet, search for a specific web page, which was static, and then you read what is there. So for most users of the internet, they didn't have any more capabilities other than just consuming. And the people who had the ability to upload all this information on the internet were people who had access to the resources like the computers. Remember, back in the day, having a computer or even a phone, a laptop was not the norm. So the people who had access to this, and most of the times they were huge organizations, were the ones who were in charge of uploading all this information. But then eventually there was the revolution of Web2, which allowed the average user of the internet to also share what they had to share. So if you're a musician, you could upload your music. If you were a painter, you could upload images of your paintings. If you are a developer like ourselves, we're also artists in our own way. You could upload your code online, upload your applications, and people could use them. You could deploy programs that other people could use, like games. And you can imagine how revolutionary that was. Like, can you imagine going from no internet to being able to share your work with anybody and consume the work from anybody? You could also go on web pages, they were no longer static, leave your comments and interact, or rather, the internet became more participatory than just passive. And the internet as it is today is actually Web 2. So as you can see, we can share our images on Instagram or other social media platforms and videos. You can share your music on Spotify today if you want. You can start creating music. You can upload your code on GitHub and many other things. You can start a blog. All of that is Web 2. And if we analyze the transition from Web 1 to Web 2, what we see is that Web 2 kind of made Web 1 obsolete. So it became a replacement for Web 1. Today, I don't think there are any static web pages, and if they're there, we really don't even know where to find them. So, Web 2 made Web 1 very obsolete, and that iteration of the internet is no longer required. That was what we call the read version of the internet, just read only, and Web 2 is read write. Now, Web 3 adds a different capability, which is we can now control or rather own our own data. Now that we can upload our data online, how do we get to control it? So with Web 2, it's all about we have these platforms or the internet itself, and we can just upload, but we have no control over what this data is being used for. Remember with that we have centralized organizations that control the storage and the dissemination of this data or this information. Today, if you upload your video on YouTube, I mean, that's a good thing, but still, the YouTube people could decide to take down your video and censor your content. So what Web3 allows is for the average user to um, be able to participate in that dissemination of information. So dissemination in this case is just like what is this information being used? How is it being propagated or published or shared online? Should it be taken down? Do we uh, yeah, how is it going to be updated? All that information. So that is what it allows. But now the problem with, I think, most people today is they think of Web3 as a replacement of Web2 because that's what we saw with Web2 and Web1. But Web3 is, I think we should all stop thinking of Web3 as a replacement of Web2 because in as much as it's now read write control, we are not going to overhaul the internet as we know it, or rather, we don't need to because Web 2 works just fine for the most part. All we need is just to add some plugins that make our applications and our experience better online. We need to be able to control our information. Yes, now we can share it, so we don't have to change that part. We just need to think of Web3 as a complement to Web2. So as you approach building in Web3, you should stop or probably avoid thinking in the direction of we have this Web2 use case. How can I make it completely Web3? Before you do that, you should think, does this require a complete overhaul or a complete change to the way it's being approached? If not, then you need to think more of how can I enhance what it does using Web3. So now that we know what Web3 is, it's really just a version of the internet that allows users or the average user to contribute their small computing power in the control of all our information. We can now dive into the different these building blocks, six of them, starting off with blockchain. So you've probably heard of blockchain a lot. And just a second. Okay, sorry. So a blockchain is basically just a distributed database or a ledger that is shared across many computer network nodes or computers in a network. So in and I'm going to keep moving between Web 2 and Web 3 so that we can understand or we can see a clear picture. So in Web 2, as we know it, we have the traditional client-server architecture. So a client is like your laptop or your phone, and you make a request to a server for information, for example, a web page. Um, this server is going to fetch some data that is stored in a database. And then if it needs to perform any computations, it will do so and then return the result to you. But all this data, of course, is being held and stored in a database. Now, blockchain, we can think of it as that distributed database that's shared by all the nodes in a network. So since we've said Web3 allows for everybody to participate, that means that different people that are geographically distributed can become a server. So they are located in different places, but logically they operate as one. So to the end user, it should be just like this system has a single server, even if it's broken up into different nodes. So each of these nodes stores a copy of this distributed database or this blockchain. And the data that is the data that is stored in a blockchain is transparent and it's immutable and it's resistant to censorship. So when we say transparent, what we mean is that it's publicly available. Anybody can query this data. Anybody can view details about transactions that have happened on the blockchain. And by immutable, we mean that it cannot be changed. And then, of course, resistant to censorship, that's meaning that we do not have a centralized organization that can take down this information or delete something that was already there or hide any relevant information based on their own needs. Blockchains differ from traditional databases in the way that they store information. So the way that blockchains store data is by linking blocks cryptographically. And we looked at cryptography yesterday, and we talked about how it enables security in decentralized systems. So this is one of the ways that cryptography is used in decentralized systems. So first of all, blockchains store data in what are known as blocks. And then for each block, it's filled with transactions. So depending on the size limit of a block, they differ. Transactions are appended. Once they are validated, they're appended to the block. And once the block is full, this entire block of data is passed through a hashing function, like SHA-256, and then we get a block hash, the result that we get, which is just a string of characters. And this string is what is used to identify the content of this block. And this string will be added to the header of the next block, basically creating a connection or a link. And that's why we have the name blockchain. It's just a chain of blocks. They are cryptographically linked by the hashes. Okay, yeah. So of course we expect that since this is a decentralized system, so I think also another thing that I want to define or make sure that each and every one of you understands is the difference between distributed and decentralized. So when we say a distributed system, we mean that the components that make up this system are not in the same place. They are broken up. Uh, it could be geographically, it could be departmentally, but basically they're just not one. There are multiple components that make up this entire system. That's what it means to be distributed. But when we say decentralized, we mean that yes, this system is distributed in a way, but there is no particular component that is superior to the rest. All of them are equal. So in this case of a blockchain or a decentralized system, every single node that is participating is equal. All of them hold the same copy of the blockchain. All of them can validate transactions. All of them can append blocks to the chain. they all have the same permissions. There's no node that is superior to the other. So in this case, all the nodes have to come to a consensus by themselves. There's no overseer or no node that is in charge of making sure all the nodes are up to date. And we're going to look at consensus as we go on. Okay. So with that, let's move to nodes. Nodes, I think I've mentioned that as we've proceeded from the beginning. So a node is basically just the computers or the different devices that are connected to this blockchain network. We've already said that we have maybe a person here in Kenya who is running their own node. There's a person in Germany who probably is running their own node. All of these are what we call the nodes, the computers, the servers that they are using to validate transactions, and they store their own copy of the blockchain. These are what we call the nodes. We just call them nodes. We don't call them computers. We don't call them servers. We just call them nodes. And they have to communicate with each other to validate the transactions and to ensure that the copy of the block of the database that they have is up to date. They ensure the integrity of the information, and they also make sure that no changes can be made unless approved. Whenever a transaction happens on the blockchain, each node has to make sure that the transaction is valid based on a set of rules, and then that transaction is added to a block, and the process goes on and on. And then once a block is added to the chain, then it is propagated to all other nodes to make sure that their copies are up to date. And a lot of the time, decentralized networks are made up of thousands of computers that are running their own software. So what you'll find is that there are different nodes in continents like Asia, there are nodes in Africa, there are nodes in Europe, in the USA, and all of them are working together logically to look like a single system. So in a traditional client-server model, we have a centralized server that holds all the data, and then the clients make requests to this server. But in blockchain networks, the nodes operate on a peer-to-peer architecture. That means that they have to interact with each other. And when a transaction is made, it is propagated to the nodes. A single node will do the validation and then propagate it to the rest through that communication. Okay, so let's move to transactions. So we've looked at the blockchain, we've looked at nodes, and while talking about nodes, we've mentioned transactions. So what exactly is a transaction? A transaction just captures details of an activity that has taken place on the blockchain. That's it. So anytime an activity happens or is performed by a client on the blockchain, that is known as a transaction. And in the case of Ethereum blockchain and Ethereum compatible chains like the layer 2s and others, there are usually three types of transactions or three categories. So we can put all transactions into one of these three categories. And the first one is transfer of cryptocurrency from one account to another. So in this case, when we see send money here, that's the money is the cryptocurrency. So transferring cryptocurrency from one account to another is a form or a type of a transaction on the blockchain. And then we have deployment of smart contracts. We will also look at smart contracts as we proceed. And then we have transacting with a smart contract. So these are the most common transactions. So if you see something like minting NFTs, this is with regards to a smart contract, because the most common types of transactions are those ones that are associated with a smart contract on the blockchain or with tokens on the blockchain. So in this case, NFTs, that stands for non-fungible tokens. That is a transaction with a token, and they are managed by smart contracts which have already been deployed on the network. Then, when you call a function on a smart contract, that is a transaction that is with a smart contract. Voting is also a transaction with a smart contract because there has to be a smart contract that's already deployed for you to vote. So in this case, there's a note here. Every transaction costs a small amount or a small fee called gas that is paid to the network for processing it. I think Lance mentioned this yesterday when he had his session. Gas is just a way of compensating the validators of the network for the work and the resources that they're using to validate transactions. It's not usually a high amount, but it also depends on the current state of the network. If the network is very busy, then you're probably going to end up paying a lot more gas than you would have paid in a usual situation. And gas fees is defined by two attributes. Though this is more technical, so I'm not going to go into deep on it, but it's defined by gas price, which is the amount per unit of computation that one is willing to pay. And then the other is the gas limit, which is the total amount of gas one is willing to spend. So that is like, of course, just the limit. You're saying I won't spend more than this. But gas price is specific to each unit of computation. And then transactions usually have attributes like an index, a transaction hash. So just like we had block hash when we were looking at our blockchains and how it's storing data, we also have a transaction hash. And a transaction hash is just a way of identifying the contents of a transaction. So each time a transaction happens, that information with regards to it is also hashed. It's also passed through a hash function. Again, we see cryptography. And the result is appended to the transaction. And if any change were to take place on the details of that transaction, it would not match with the hash that was appended. So obviously we'll know that there has been some tampering that has taken place. So it functions just like a block hash. Then also we have attributes like the sender address, which is, of course, the wallet that initiated the transaction. We have the destination address, which is the recipient. We have amount, which is the amount usually in the native cryptocurrency. So if you're on Bitcoin, it's in Bitcoin. If you're on Ethereum, it's Ether, and all the other chains. That is the amount in cryptocurrency that is to be sent in this transaction. And then, of course, we've already talked about fee and other details like data and events. Data can be, it's binary information that can be like the address of the contract that we're calling, the function that we're invoking, a message to the receiver address, a specific message, or contract code in the case of deployment. Yeah, so that's about transactions. I think before I proceed, I'll just ask if anybody has a question up to that point. Thank you, Abraham. Is there anybody who has a question? I hope we are clear up to that point. If anybody is confused, feel free to stop me. So up to that point, we've seen blockchain, nodes, and transactions. So a transaction happens,
So
it's validated by, yes, go ahead. Go ahead.
yes, yeah, I think so. You've said that we can dissect many data and all that. But can it be the same case if you're trying to dissect image? Is it possible? Maybe captions. I don't know if it's possible. I'm just curious.
Wait, I can't hear you very clearly, even if it's just me. Could you try again?
Can you hear me?
Yes, I can.
Thank you so much. Yeah. So can transactions also be in form of, let's say it is in the energy space or healthcare? Can, for example, someone trying to transfer, say, energy, because I'm trying to build a closed pathway. Um, is it possible, or it has to be from NFTs? Yeah, even in either in health or energy space.
Okay. Okay, I think I get your question. So you're asking if it can be related to any other industry, right?
Yes.
Okay. Yes, it definitely can. So as I've said, with the transactions, there are three types of transactions. There is the transfer of cryptocurrency from one account to another. So that one is specifically for financial transactions. And then there's the deployment of smart contracts and transacting with a smart contract. So in the case of energy, first of all, you would need to write a smart contract, and we're going to look at the concept of smart contracts. You would need to write a smart contract that implements the logic that you would love to have on chain. And then from that point on, other clients can interact with this smart contract that you've deployed. And this is the third type of transaction, which is transacting with a smart contract. And in this case, the client can invoke a specific function in your smart contract. So, for example, if it's maybe you have a function for carbon credits, I don't know, let's just call it something like that, right? They can invoke that function, and then if the conditions that are met, the conditions that you set in your smart contract are met, then a specific result will take place on the blockchain. So yes, it can apply to honestly any industry as long as you have a smart contract and you deploy it on chain. Even in the case of tokens, those are handled by smart contracts. They are actually just smart contracts that handle all of that. Okay. Yes, Ochi.
Yeah, so I think the easiest way to define a smart contract is changing the state of a record on a database. No, I mean a transaction, sorry. Am I right, Lynette? Like just changing the state of a record, that in itself is a transaction. So then that could now be a financial transaction. It could be that you're updating the record of a token balance, or it could be something else. But I think that's the easiest, most simplest definition. I think I'm right,
Yeah.
Lynette, right?
Yes, you're right.
Yeah.
Okay. Any other question? I think somebody else had raised a hand.
Yes, it was me.
Okay. Yes, go ahead.
I have posted the question in the chat. Earlier you mentioned that Web3 should enhance existing systems rather than replace them. In your experience, what are some examples where decentralization adds genuine value, and what are some cases where traditional centralized approach remains the better choice?
Okay. I think for this question, I'll answer as we wrap up so that we can just move on to the next part of the agenda, and then I will get back to this towards the end. Okay, so if there's no other question, could you pardon on the intro? Which part of the intro?
Oh, okay. I managed to join halfway. So could you just pardon? Because I don't understand the content somehow.
Okay, I'll just do a brief recap of what we've covered so far.
Hold on. Before you go on, Lynette.
Yeah.
Ursula, maybe you can just let us know where we dropped off so that we know how to
Okay.
pick it up. Yeah.
I just joined when you guys were in the fourth slide. So I joined you when you were in the fourth slide,
This
not
one.
at this. Yeah. So I didn't understand the first slide. What you discussed about left me hanging. Would you please pardon?
Okay, so this was actually the very first slide. The slide before that, we just did a brief foundational overview of Web3. So just to recap what I've said, we've talked about the different iterations of the internet, which is Web 1, Web 2, and Web 3. Web 1 is the earliest onset of the internet, which allowed people to access a massive repository of information. So it was just consumption. You could log into the internet and read what was already posted by the people who had access to resources. You couldn't really interact with this information. You couldn't leave your own sentiments if it's like comments or likes. You couldn't do anything beyond consuming. And then after that, it evolved to Web 2, which is now read-write version of the internet. Not only could you consume, but you could also upload your own information or your own data, your own content. You could create. We all became, or we all had the ability to create and share our creations online. So in terms of uh, educational content, music, art, code, anything really, you can share all of that online. You can leave comments on other people's content, and that's now Web 2. It allows each and every participant of the internet or user of the internet to contribute in their own way. And then we looked at Web3 and we said that Web3 allows the average user of the internet to participate now in controlling this information. How do we control the propagation of this information? How do we make sure that it is resistant to censorship? How do we make sure that it's not being used for all the wrong purposes when it's being controlled by centralized organizations that have the servers? Now anybody has the opportunity to join the network and contribute the little computing power that they may have in order to make sure that the data that we have online is safe and secure and it's being used for the right purposes. It makes the entire experience of the internet better for the average user. We also mentioned that in as much as Web 2 came and replaced Web 1, we shouldn't think too much of Web 3 as a replacement of Web 1, rather as a complement or an addition, a plugin that makes Web 2 as we know it even better. So that's what we had for the initial slide, and then we moved into this one. Is that okay?
Yeah.
Okay, nice. Okay. Okay, so with that, I'll move to consensus. So we've looked at nodes specifically. We've talked about decentralized nodes, decentralized. The decentralized system is made up of many computers that are geographically distributed, and they're also decentralized, meaning that there's no superior node to the others. And in order for these nodes to come to an agreement on the current state of the blockchain, they need to be able to communicate, and there also need to be some rules that enforce what a valid transaction looks like. So it's a consensus, or a consensus mechanism is basically just a set of rules that allow a distributed network of computers to agree on the current state of the blockchain. And when we say current state, it can be something like Alice's account holds 5 Bitcoin. And then when a transaction happens, Alice sends 2 Bitcoin to Bob. Her account now is at 3 Bitcoin. That is the current state of the blockchain. And all the nodes of the network need to agree that based on the initial state and this transaction, this is the resulting end current state. They all need to agree. That's a simple example. And in that way, we can actually think of blockchains as a finite state machine, but that's beyond today's concept. So usually in centralized databases as we know them, an admin is the one who has the final say on data updates and what is currently being held in that database. But in decentralized systems, there is a challenge. It faces a challenge when it comes to these nodes agreeing on the current state. And this challenge is usually called the Byzantine Generals Problem. I'm not going to go into that today. You should actually read it on your free time. It's quite interesting. And sorry, it defines the logical dilemma that decentralized nodes face when it comes to arriving at an agreement without a central coordinator. So in a decentralized system, logically, it sounds like it could work just fine. But when you actually implement it, you find that some nodes end up being offline or they face some challenges during the operations of the network. How do we ensure that the network still keeps validating transactions and updating the blockchain? Additionally, we can have nodes that are malicious. They have ulterior motives. They're probably looking for ways to exploit the network. How do we make sure that the network still stays resilient and transactions that are appended to the block are still considered valid? That is implemented using the consensus mechanisms. And they usually implemented, or rather, they provide a mathematical and economic guarantee. So when I say economic in this case, we're talking about game theory, whereby we're assessing the when it comes to a node, how much do they have to lose that will incentivize them to act with the best interests of the network at heart. So when we are implementing a decentralized system, we need to make sure that we're implementing it in a way that every single node is incentivized to act in the right manner. So these consensus mechanisms, they follow mathematical principles and also economic principles. And in that way, it reduces the trust that you need to have in these nodes. You don't need to trust that this node is going to look at my transaction and see that it's valid and then append. Maybe they have their own different agenda. But now you're trusting in this consensus mechanism that is mathematically secure. And you know that whether the node is malicious or not, a valid transaction is going to be appended on chain. There's not going to be any changes or tampership or censorship in any case because there are those guarantees. So some common or popular consensus mechanisms, we have proof of work that is used on Bitcoin. In this case, we have the nodes doing a process known as mining, which is basically solving complex mathematical computations in order for them to propose the next block of the chain. And usually these computations require really powerful machines because, of course, they're computation intensive. They need you to have a machine that has a lot of memory, that can handle really tough mathematical puzzles. So with proof of work, if a node is able to propose a valid block, a next valid block, then that means that they have actually contributed their resources, they have used their resources, and they are going to get rewarded in the native cryptocurrency, which is Bitcoin. But in the case of Ethereum, the consensus mechanism that is used is proof of stake. So in proof of stake, we replace miners, or these nodes are now known as validators, and they have to lock up some amount of the native currency. So in this case, it's Ether. They have to stake this amount of ETH to the network so that they can be able to validate transactions. And this is the economic situation in this case. If you stake a huge sum of ETH and you act maliciously, you're going to get slashed as a validator, which means that you no longer have the permissions to validate transactions, but you also lose your stake. So imagine if it's a lot of ETH, you would definitely not want to lose that amount. So you're going to act in the right way or as expected. There are actually many other consensus mechanisms, like this delegated proof of stake that allows people to vote for the specific validators that they want based on an amount of stake that they have. There's nominated proof of stake, and there's others. There's many, but the main ones are proof of work in Bitcoin, proof of stake in Ethereum. Okay, so yeah, now here we look at smart contracts, finally here. Okay, so smart contracts are basically just computer programs that are hosted and executed on the blockchain. It's as simple as that. We have computer programs, probably if you're a developer, you have written some code yourself. That is a computer program. And for it to, when you host it on the blockchain, it is considered a smart contract. And by running on a decentralized blockchain instead of a centralized server, so in this case, instead of having it in like Web2, you now have it in Web3, the smart contracts allow multiple parties to come to a shared result. So these parties are the nodes, and they can come to a shared result based on the logic of that smart contract in an accurate manner. And smart contracts are also good, or they're a very good use case for automation, because there's no central party that is going to make sure that now this condition has been met. So can the code run? Can this function run because the conditions have been satisfied? No, it just happens automatically. So the logic of smart contracts is usually in the form of if statements. So if you've written some code in Python, whatever, you must be familiar with if statements, which you say if or when X event happens, then execute some Y action. Or if this happens, then do that. So in this case, we don't need anybody who is enforcing this code as long as we have it on chain and the conditions are met. So whenever a function in our smart contract is invoked or our smart contract is called to the smart contract address, the conditions are checked. If they are met, then a particular action or event takes place. So a smart contract can have multiple different conditions, not just a single one. So depending on what you want to achieve with your smart contract or with your code, just think of it as code, you can have multiple conditions, and one application can have multiple smart contracts that support different processes in your application. So yeah, that's pretty much it. So in the case of smart contracts, you can think of any industry. They can apply to any industry, in as much as we may have smart contracts that handle tokens on chain. So we have smart contracts for NFTs or for different other kinds of tokens that we find on chain. You can also have smart contracts that deal with maybe supply chain records. You can have smart contracts that deal with healthcare records or energy records, as we've had so far, and so on and so forth. The use cases there's so many. Okay. So the sixth building block is wallets. And a blockchain wallet is basically just a piece of software that enables sending and receiving cryptocurrencies. And usually it stores the records of the transactions that have happened and that relate with this account. And it also has the public and private keys that are used to perform these transactions. So public private key for transactions, this is asymmetric encryption in cryptography. So again, we can see cryptography being used in wallets here. And you can think of a public key as your account number. If you have a bank account, you have an associated account number, which identifies your account. And you can give this account number to another person and tell them, send money to this account. So that is your public key in this case. Anybody who has your public key can send you some cryptocurrency. And then for private key, you can think of it as your password. It allows you access to the assets that are held in your wallet. You can control them. You can spend the cryptocurrency that's in there. You can initiate new transactions and sign them with your private key. So your wallet holds these keys, and just like the name suggests, your private key should be a secret. You should not share it with anybody else, because once another person has your private key, they also can control your cryptocurrency and your other assets. Maybe if you have some NFTs in your wallet, they can also control them for whatever the reason they know. And of course, for any transaction to happen, or for it to get to a point where it needs to be validated by the nodes, as we've mentioned before, then you need to sign this transaction using a private key. So that is a cryptographic signature that confirms that this transaction has come from this specific public key. Public key and private keys come as a pair. It's just like a lock and a key. They cannot be separated. If you don't have the private key to the corresponding public key, then there's not much you can do with that public key. So if you sign a transaction with your private key, then it can be, your public key can then be used to confirm that this transaction was signed by the corresponding private key. And then we can talk about types of wallets. So in terms of types of wallets, of course, we have this, what's on this slide, this custodial and non-custodial, but we also have the hot storage wallets, which are like the software wallets, and they are the wallets that are usually connected to the internet at all times, and they allow the user to easily access their accounts and perform transactions. So examples are like what are on my browser up here. Can see MetaMask. There's MetaMask right here. They're just software wallets that you can access from perhaps your browser, or you can even install applications for these wallets. So all of these are the hot storage wallets. And the problem with these ones is that they're vulnerable to attacks because they are always online. They can easily be attacked, exploited by attackers, sorry. And then we have the cold storage, which are hardware wallets. And just like it suggests, it's a piece of hardware that if you need to use your account or access your account, you would have to connect it to your computer or your machine, and then you can perform your transactions, you can access your assets, you can do whatever. And then once you're done, you disconnect. So of course, the advantage is that they're not always online, so they're not that susceptible to attacks. And then a different kind is the multi-signature wallets, which allow multiple parties to initiate transactions or to perform transactions together. So once a transaction is initiated by a single party in that multi-sig, they're called multi-sigs, then there would need to be a threshold amount of signatures, and the threshold is set in the beginning. So say there are 5 parties, we can say that for a transaction to go through, 3 out of 5 need to sign this transaction. And once those 3 are met, the transaction goes through. Otherwise, it will not. Then we have, in the case of custodial wallets and non-custodial wallets, these are the ones that are controlled by exchanges. They're custodial because someone else is the one who holds your keys. They're not in your control. And they're often provided through exchanges. We have the non-custodial wallets, which are like the MetaMask. So they allow you to hold your own keys. In the case of your secret key, or private key, you're the one who has access to it and control over it. And of course, they're safer because nobody else can access them. And they also require you to be more aware and more responsible. Yes, so now we can put all of this together. All these 6 building blocks that we have looked at so far, we can put them together in this way. So when we have our wallet, we can log into or create an account in our wallet, and then we can initiate a transaction. So when we have our wallet, we have access to our private key. We need to initiate a transaction. Say, I want to send Bob 5 Bitcoin. I will initiate the transaction from my wallet. I will sign it with my private key, and then it will go to the nodes for validation. The nodes will then check against specific rules, which are the consensus mechanism, to make sure that my transaction is valid. Once it is valid, they will add it to a block, the current block that is being edited. And then once that block is full, it will be hashed and then added to the chain. And then in the case of smart contract, we would have to think of maybe a different kind of a function, maybe record vehicle insurance policy. So that is the transaction that we want to initiate from our wallet, sign it with our private key. The transaction goes to the nodes. They check against the, of course, if the conditions are met for this registration to happen, then the transaction will be validated by our nodes against a set of rules and then appended to the blockchain. Pretty much is the process that we're always going to, or is always going to be happening in the back when you have your decentralized applications on chain. And once you understand these fundamental building blocks, then you can be able to understand how every decentralized app works, how you can build your applications, how you can maybe organize the logic in your smart contracts. So pretty much that's it. So now we can move to questions. SB type that here. Irene, I don't understand your question.
Oh, no, it's actually been answered. I was just saying somebody to type what you had mentioned and they've typed it. Though I do have another question. My question is with maybe examples of custodial wallets, because I feel like I'm more like conversant with non-custodial ones, but I can't like grasp the idea of what a custodial wallet kind of looks like. And finally, the other question is you said that in your notes at least there was a place where on smart contracts it says that it's code that executes itself. And I'm just curious if you would explain that further. Why are we considering it code that executes itself?
Okay. So I'll start with this one. And we've said that a smart contract is basically just a computer program that is hosted on chain and it's executed on chain. And when we say it executes itself, this is the automation or the automatic part. Since we've said that our code is made up of if statements, if a certain condition is met, then a specific action is going to be executed. So that is what we mean when we say executes itself. We just check, not us, but the smart contract now is checking that a specific set of conditions is met, and these are the conditions that are set by the developer as they're writing the smart contract. Once they are met, then the rest of the code will just execute. There is nobody who needs to be overseeing the process, just that these conditions, as have been directed, have been met, therefore the code will proceed. And then for custodial wallets, we have different exchanges. Like, I don't know if you've used exchanges like Binance, there's OKX, there's they allow you to have some wallets that can hold cryptocurrency in them. Okay, let me check the chat as well. Okay, yes. So as Ochi has said, we'll have the Byzantine Generals Problem as an assignment. I really think you should look into it. I think it's very, very interesting. It's not only related to decentralized systems, but generally just distributed systems. So even in Web2, we usually have distributed systems when it comes even to the entire network or computer networking. When it comes to databases, not just in the case of blockchain, you can also have distributed databases in Web2. And basically, this is a problem that affects all kinds of distributed systems. And I think it's very interesting. You're going to love the read. Okay. If I may, I think our street. Okay, yes. So consensus mechanisms. Yes. So yes, you can think of it that way, and I think that's a more technical way of thinking of it. Of course, when we're thinking about it in this foundational sense, we can just think of proof of work and proof of stake and other different kinds of consensus mechanisms as just that. But it definitely goes deeper than just describing them as consensus mechanisms. So I guess we'll just avoid that technicality for now. Can we say a wallet is a database in a blockchain? Not really. Maybe loosely we can, because it also holds a record of all the transactions that specific wallet has been engaged in. So we can say loosely it is. And it stores a record of maybe how much cryptocurrency you own. So if it's a Bitcoin wallet, it holds a record of. So yeah, we can say maybe loosely, but it's not exactly a database. Okay. So if there's no other question, I'll move back to, okay, yes, McBride, I think. Go ahead.
Okay, hi everyone. I have a question. Do torrents use the blockchain type of technology?
Torrents, I'm not sure of that. I don't think I'm the right person to ask that. Maybe you can explain. Yeah,
I can
go ahead.
contribute. So actually, torrents was one of the first peer-to-peer type of networks. So they share the element of decentralization, in that you've got nodes, and these nodes are keeping packets of data, right? And in that sense, the peer-to-peer network of a torrent acts almost like a single server, although the nodes are distributed. But where I would say maybe there might be some differences. I'm not so sure if torrents are encrypted. I don't think they are. I'm not sure. But what makes blockchain what it is all these elements that it brings together, which is you've got decentralization, then you've got the encryption of like data, and even the hashing of the connection of the nodes, and the transparency of the ledger, and such things. So they're like creatures of the same type of animal, I guess, but not exactly the same. I don't know if that makes sense.
Yeah.
Okay. Any other question? Okay, so I'll go back to David's question in the chat. He said you mentioned that Web3 should enhance existing systems rather than replace them. In your experience, what are some examples where decentralization adds genuine value? And what are some cases where a traditional centralized approach remains the better choice? Okay, so I think some of the use cases that have experienced the most success when it comes to decentralization is, of course, number one is decentralized finance. Because, of course, when it comes to our finances, it's a very sensitive topic. We do not want to be at the mercy of centralized organizations. So a lot of people, a lot of organizations are trying to solve the issue of having to rely on centralized organizations to carry out financial transactions, to store our finances or our money. In the case of like banks, they're the ones who are in charge of our funds. We have to deposit there, and they can mess you up. It happens all the time. So one of the use cases that has found the most success with decentralization and fully or entirely is decentralized finance. Another one is something like supply chain. So when it comes to tracking the origins of raw materials, whether it's food or anything, it probably is among the very first use cases of blockchain and decentralized systems. So that decentralization aspect, the immutability that is offered by blockchains in terms of our records. When we have our records, they cannot be tampered with. It provides a clear, transparent follow-up that everybody has access to. We can tell where our raw materials are from. So in the entire supply chain process, that is also a big use case of decentralization. So in terms of cases where traditional centralized approach means a better choice, I don't, I think for the most part,
I can
yeah.
think of like if you send money to someone by mistake, you can have M-Pesa reversal. Okay, I guess you can do a reversal. But you could call that into a smart contract. But the thing is, with blockchain, it's like it's on you, right? So there's no one to call when there's an issue. There's no one to help you, like retrace transactions and stuff. So everything is on you. So the security is on you. Like the benefits are there, but then also the disadvantages of not having someone to come and help you with let's say like reversing a transaction maybe.
I have a question, Ochi. Recently I used Minisend and I had an issue, and Chris, the founder, managed to sort of do a reversal. What was that? Because I think I was left a bit confused. I thought if you're using a DApp, that's it. And you encounter an issue,
Exactly. So
that's it, it's lost.
Minisend is a custodial wallet, right? So you don't necessarily hold your keys. As much as the technology runs on blockchain and there's all these smart contracts everywhere, ultimately they are not fully decentralized. So a fully decentralized wallet is something like MetaMask, where once you do that, that's it. Like you're done. There's no customer care number to call. So building on blockchain does not necessarily mean that all your like how do I put it? Like there's blockchain tools like smart contracts, right? There's ledgers and you can verify transactions. But then the nature of custody is what I think will determine whether you're fully decentralized or not. Lynette, you can correct me if I'm wrong.
Pardon?
Oh no, I was saying the nature of of custody is what would determine whether you're truly decentralized. Well, it is one of the measures of true decentralization.
Yeah.
But yeah, it doesn't have to be like, it really depends on what you're trying to achieve, If you're a business and you're just looking to make your customers happy, yeah, then sure, you could have custodial wallets. But if you're, I'd say, a purist, like guys in Bitcoin don't believe in any of this, it's actually Bitcoin doesn't believe that any other chain is decentralized actually. But that's a whole thing you guys will get into as you get into the community and the culture of crypto. It's another whole thing. Did I answer your question?
Okay, nice. Thank you, Ochi and Rosalie and Washuka. So there's also some questions in the chat. Could you please touch on the private and public keys a bit? Yeah, so private and public keys are used in encryption of data, and it's a form of asymmetric encryption. Asymmetric means that two keys are used. There's a key for encryption, and then the other key is going to be used for decryption. So when you create a new account, maybe on MetaMask or whatever wallet that you're going to create, then this pair is generated and they are linked to each other. So in the case of, for example, you want to prove that a specific transaction or a specific piece of data, for example, comes from this wallet, then you can encrypt it with your private key. And then another person who has your public key, remember it's accessible to anyone, they can decrypt using that public key. And if it succeeds, then of course that data came from that specific wallet. Otherwise, if you want to send maybe a specific transaction to this wallet, you can encrypt it using the public key, and only the private key can be used to decrypt. So if one is used for encryption, the other that is linked to it is the only one that can be used for decryption. And there's not one that is specifically used for encryption and the other for decryption. It just depends on your goal. If you want it to only be accessed by maybe one party who has access to a private key, then you would encrypt to the public key. But if you want to prove that it's from a specific party and can be accessed by anybody, then you would encrypt to the private key and decryption would happen with the public key. That's pretty much it about the private and public keys, and it's used for a lot more than just wallets. This is just one of the use cases. And then another question. I hope I've answered your question, Anita. Then another question is, what does layer 1, layer 2 mean in blockchain? Okay, so when it comes to blockchains, there are these layer 0, there's layer 1, and layer 2. So layer 1 are the blockchains the decentralized systems where transactions actually happen. So Bitcoin is a layer 1 blockchain. Ethereum is a layer 1 blockchain. Cardano is a layer 1 blockchain. So it's where all the transactions are actually happening. And then as we've proceeded with building blockchains and counter different kinds of problems, people have ended up creating the layer 0s and the layer 2s. So layer 0 is, you can think of it as a foundation or as a building block that allows spawning of layer 1s to become easier. So layer 0s are generic. They provide the security that you would need. So when you're building your layer 1 and you build it on top of an existing layer 0, you would not have to do the intense work of implementing security because that will be handled by the layer 0. So when you're building your layer 1, it will be easier because you'll focus more on the functionality that you're trying to implement. Building a blockchain is not easy at all. So it's like now you've made a module that somebody can just come and add to their own layer 1 to make it easier. And then in the case of layer 2s came as a result of scalability issues in layer ones. So let's use the example of Ethereum. There's this problem known as the blockchain trilemma that focuses on three characteristics. That's security, scalability, and decentralization. And the blockchain trilemma states that you can only achieve two out of these three. So in the case of Ethereum, it usually, or rather, it has prioritized security and decentralization. So the more nodes join the network, the more decentralized that network is, and the more secure it is, because every transaction now has to, or there are more parties that are participating. So the system is obviously more secure. But in a case of a system where we have a lot of nodes, then that system cannot handle a lot of transactions because it becomes slower. And that affects, of course, the scalability of that network, which is the case with Ethereum. So layer twos are just blockchains that a lot of the times they handle the processing of transactions so that they can make the layer one faster. They can make transactions that are happening on the layer one faster. So we have different kinds of layer twos like Stacknet, we have Optimism, we have Scroll. Scroll is a layer two, right? Base, yeah. They handle the scalability, or they try to solve the scalability problem that is experienced on a layer one like Ethereum. Yes. Another example of a layer zero, I've not given examples of that, is of course Polkadot, there's Avalanche. Yeah. There's what's it called? I've forgotten the name of the other. Yes. Cosmos. Yeah, it's called Cosmos. Yes. I hope I've answered your question. Joshua. Okay, any other question?
Yes, yeah, I hope I'm audible. Am I? Yeah, thank you so much. So you've mentioned about the hardware wallets and how you could, put them in contact with your computer so that you can do transactions and all that. Do you think that could be the same case if you're trying to like do a transaction, say an energy meter or rather, or do you think the wallet could also be like expanding the energy meter? Or I mean, if you design the energy meter to be in a manner that it can scan, do you think or do you think it's possible? I'm just curious.
Mm-hmm. If it
An
can,
energy meter,
an energy
energy
meter
meter. Yes. I mean, you
to
mentioned about
be,
the hardware wallets, so they have
uh,
to be in contact with the computers and all that. Are you excluding other devices such as the smart meter or other? I don't know. What do you think?
uh, no. Okay, so in the case of hardware wallets, remember we've said that the hardware wallets are really to do with cryptocurrencies. So, receiving and sending, and also initiating transactions or signing of transactions. So, uh, maybe you can start from that foundation when you're trying to think of that. So, what would the energy meter be doing?
Um, I'm still on aviation stage. I just think about that. Thank you.
Okay. Yeah. We can keep brainstorming as we go. Okay, so if there's no other question, then that was my presentation. Thank you for joining, and I hope to see you guys throughout the cohort. Yes, and you'll eventually see me. I know you wanted to see me today.
You must be seen.
I must be seen.
Yeah, thank you so much, Lynette, for that. It was an engaging presentation. I hope you guys enjoyed it. Yeah, time has passed. We had a breakout room activity, but maybe we can save it for other sessions. Yeah, if we don't have any more questions, for those of you who are here, I'll make the announcement in the group, but we have one more session tomorrow to cover or finalize the blockchain fundamentals. You've seen how broad it is, and in 2 months, you're required to ship something or demo something. Next week, we'll handle AI fundamentals. So we'll cover fundamentals of AI, everything to do with models, all the way to coding agents. And heads up, our sessions are gonna be on Monday, Wednesday, and Thursday, right, Ochi? Monday, Wednesday, and Thursday. So again, I'll make the communication.
Yeah.
We'll also roll out the full curriculum. Yeah. Yeah, we'll also roll out the full curriculum. Right now, just consider it the foundation. It's gonna get really heavy, but hopefully you'll get better as time goes. If there's no other question, no other comment, I think it's safe to call it a night, and we'll see each other tomorrow. Thank you so much, Lynette. Lynette, maybe you can share your handles in the group or any other way for guys to do you want us to reach out?
Yes, sure. Okay, I'll share in the group.
Okay, so you get Lynette's handles and slides as well. Thank you guys for joining. Have a lovely evening and see you tomorrow.
Bye.
Yes.